we're going to start off the morning with a little bit of a workshop about analyzing contextual data and then some of the best practices that we found in using the CDR data products in our research projects. And so I know that we have kind of a lot of different types and levels of expertise in the room. So I'm hoping that we can kind of have a discussion going as we work through these slides. So feel free to raise your hand as we go along. If you're on Zoom, we have someone monitoring the chat, or you can go ahead and just turn on your mic. And then at the end, we will also have some dedicated Q&A time as well. So we're going to first start with some data management best practices. How do you get your contextual data linked to your individual level data and ready for analysis? Eun-Young is then going to join us for some data visualization, and then we'll end the session on some model estimation. All right. So when you're about to kind of embark on these contextual data products, you normally have two types of data that you're looking to merge together, right? So for us, that might be your contextual data with the CDR data products, but maybe you're also using some of your own contextual data that you've collected or some census data that you've been working with. And then you're hoping to link that data to individual level data. That might be the health and retirement study. A lot of people in the room use that. But as Jennifer mentioned yesterday, we also have the UAS, the Understanding America study, and also the NHATS. These are all available on that MICTA GLR repository and are useful for this type of research because they provide information about where the respondents are living. And so you're able to use that information to link the individual data to the contextual data. And we do that linkage by identifying a common data element across both of the data sets. And in this case, that's going to be your geographic identifiers. In other sorts of data sets, you're maybe doing like schools or classrooms or things like that. But for us, it's going to be those geographic identifiers. So if you have your contextual data with identifiers and your individual level data with identifiers, then you're pretty good to go, right? You're on track to linking your data appropriately together. If you're doing work within the US, a very common geographic identifier that we use is what's called these Federal Information Processing Series codes, or what we call FIPS codes. These are numeric codes that are assigned to multiple geographies. So there's FIPS codes for state, for county, even all the way down to voting districts. For the CDR data products, most of our products are at the census tract level. And so if you're using the CDR products, you will probably see this 11-digit census tract FIPS code as the geographic identifier that you will use to merge in your individual level data sets. And so here's an example of one of those census tract FIPS codes. And if you're not familiar with these codes, it's helpful to know that they are made up of a couple different elements. So the first two digits of your census tract FIPS code is going to identify the state that the census tract is located in. So in this instance, 06 refers to the state of California. Every state in the United States is given a 2-digit FIPS code, and that code uniquely identifies states across the US. So if you're doing a state level analysis and you have a 2-digit FIPS code identifier, then you have a unique identifier for states in your geographic data set. The next 3 digits of the FIPS code refers to the county within the state that the census tract is located in. If you have a 3-digit county code, FIPS code, that does not uniquely identify counties in the United States. So a 037 county in Los Angeles, or refers to Los Angeles County, but a 037 county in Alabama might refer to another county, right? And so to uniquely identify counties in the United States with FIPS codes, you need the combination of both the state FIPS code and the 3-digit county code to have a unique identifier at your geographic level. And so that's useful to know. In the CDR data projects, we provide the 5-digit county code that's a unique identifier, but some of your contextual data might not. They might just provide you with the state FIPS code and the county FIPS code, and then that's your responsibility as you're preparing your data for analysis to merge those identifiers together to create that unique identifier. And then finally, we have the actual census tract ID. So the census tracts really don't get like fancy names like Los Angeles County. They just get a numeric code. So here, census tract 2227.00. That is the current census tract that we are in here at USC. And similar to county, if you have this 6-digit census tract ID, it's not going to uniquely identify your census tracts across the US. You need both the 3-digit county FIPS ID and the 2-digit state ID to create an 11-digit unique census tract identifier. For some of you that might be interested in lower geographies like the block level, that's going to be a 12-digit identifier, and there'll just be an extra digit onto this 11-digit identifier. Any questions on that? Okay, so something that came up yesterday that we'll talk more in detail about today is that you might have these FIPS codes in your geographic data set, in your individual data set, but you need to know that these geographic boundaries can change over time. So depending on your sort of temporal scope of your data project, it's good to know what's happening at the geographic level to make sure that you're doing a correct linkage and that you're identifying the right census tracts or the right counties, or, well, states don't change as much over time, but the right states as well. So in terms of census tracts, this happens actually quite frequently over the years of census tracts, census tract boundaries changing. So here's an example of a census tract in Madison County, Georgia, where in 2019, you can see we have a 020-500 census tract, but then by 2020, that census tract is split into a 01 and a 02 census tract. And this is happening pretty frequently and pretty widespread across the US. So between 2019 and 2020, you see about 16% of census tract changing their boundaries in some way. Jennifer mentioned this briefly yesterday, but just to reiterate, for the CDR data products, we have gone ahead and harmonized the census tract boundaries to a particular year. So in almost all of our data products, we're going to provide you the harmonized 2010 census tract boundaries. But for products where we have more data, so for instance, the census data products, we also provide the 2000 and the 2020 census tract boundaries or county boundaries. But again, your other contextual data that you're using might not do this work for you. And so that's something also to consider as you use other contextual data sources, is to know what boundaries, what year boundaries your FIPS codes are referring to. And so here's just a little snapshot of the number of counties and census tracts between 2010 and 2020. And I wanted to show this table for two reasons. So one, I think it pretty clearly shows the differences in geographic boundaries for census tracts. We have about 10,000 additional census tract FIPS codes in 2020 compared to 2010. But when we go to the counties, the kind of counties, it's a little bit more unclear. So for here, we see that we have the same number of counties from 2010 to 2020, but you would be mistaken to think that those are the actual same county boundaries from 2010 to 2020. So especially in Alaska, we see some county changes happening in 2015 that result in the same amount of counties overall. But are not necessarily the same geographic entity that they were in 2010, right? And so you really have to be mindful of that as you're approaching this type of analysis. The second reason I wanted to show this table is it's just helpful to have a geographic kind of scope of your data products. especially when you're doing data linkages with other contextual data sources. So as you're merging, county level data to other county level data or census tract data to other census tract data, it's helpful to have an idea of how many matches you're expecting to have across cases, right? If you do a merge and you realize you've only matched 1,000 counties between two contextual data sets, you know that maybe you've had an error in your coding because we would expect to see at least 3,000. And so along the same lines, you also need to know your geographic scope in terms of what is your kind of coverage of your research projects. There's different variations of how we can study counties, census tract states across the US. In our CDR data, we always include Puerto Rico whenever we come across it in the raw data. So if the census data is providing Puerto Rico, we go ahead and aggregate that data as well. But again, your other contextual data might not do that, right? And then similarly, your individual level data that you're linking might not be representative of all US counties, all US census tracts, right? So we don't have HRS respondents in all of the census tracts in the United States. And so when you're doing your linkages to your individual level data, you might have cases that aren't matched because of the sampling frame of your individual level data or because of the geographic scope of your contextual data, right? Okay, so number 3, when you get to merging your contextual and individual data, using those FIPS codes and those geographic identifiers, a really common hurdle or mistake that we see new users make, especially, is inconsistencies with formatting of your FIPS code across your contextual data set and your individual level data set. So in your STATA program, in your R program, you're storing your data values as typically either a numeric type or a string type. If you're in a string format, you're in a text format, and you're going to have that full 11-digit identifier of the census tract. And it's going to have this leading 0 for a number of states that have census tract or have state FIPS codes below 10. When you're in the numeric format, STATA or R is going to drop that leading 0, and you're going to be left with a 10-digit census tract identifier. This 10-digit census tract identifier is still unique to census tracts. And so STATA, especially because, STATA likes to give you like error messages a lot, right? STATA is not going to give you an error message if you do this merge because you have a unique identifier at the 10-digit level with these census tracts. And so you'll just have a bunch of mismatched cases after you do your merge because you've essentially not matched on about 10 US states or census tracts within 10 US states, right? And so that's really important to keep an eye on. You want either the 11-digit string format in both your contextual and your individual level data, or you want that 10-digit numeric format in both your contextual and individual level data. We've also found that sometimes we have mismatches in our linkages due to the individual level data set. So with the HRS, we found that there are some respondents that just have incomplete or inconsistent FIPS codes. So they'll have like an 8 or a 9-digit FIPS code. And so those obviously do not get matched to the 11-digit or 10-digit code from the contextual data source. And so that's something also to keep an eye on, that you might have some like stragglers that just you can't capture because you can't assume that they're living in one census tract versus another. Whereas perhaps if you're doing a county or a state level merge, you might be able to capture these people in your linkage. All right, so once you're ready to merge, we can just use that geographic identifier in either a cross-sectional or a longitudinal framework. So in the CDR data products and in the HRS geographic detail file, that geographic identifier for the harmonized 2010 census tract boundaries is named link sen 2010. And so we use that variable to employ our merge command in Stata. You do whatever you do in R. I'm not a Stata, I'm not an R user, but I'm learning. So in a cross-sectional format, you're just using that geographic identifier by itself. If you're in a longitudinal format, you can go ahead and use that year variable in addition to the geographic identifier to get a unique combination of an identifier for each observation in your data. Because for our individual level data, we often have multiple respondents that live in the same census tract. You're almost always doing a one-to-many merge or a many-to-one merge, depending on your order of operations. And then finally, we've thought about we have some kind of like strategies that we've employed to make sure that we're merging accurately and correctly across these geographic data files. So for instance, something that came up yesterday that a lot of people would mention in the Q&A of the different research projects was that, you wanted to think about urbanicity, or you wanted to think about differences in affluence and disadvantage or something like that. And so oftentimes that requires merging multiple geographic data files together. You're not just pulling one air pollution data set or one heat data set. And so when you're doing multiple data merges, we find that it's really helpful to do those higher order merges first. So you would merge at maybe the state level first, all your state level data, then you merge all your census level data. And then finally, you bring in that individual level data. Primarily, we do this because going back to the counts of expected counties, expected census tracts that you would see for the US, when you get your summary of your merge in Stata, or perhaps you can get a similar table in R, you're able to interpret that summary table if you know what your sample is, right? If you know I have 70,000 counties, I have 80,000 or 70,000 census tracts, I have 3,000 counties. Once you bring in that individual level data, especially if you're in a longitudinal format, you now have a bunch of cases that are getting merged onto the same geography, right? And so that summary table becomes much harder to interpret, and it becomes much more of a challenge to just eyeball and say, yeah, I've done a good job, or no, I have to go back and check to make sure my linkage ran correctly. And so that's kind of the last little tip that I'll leave you with in terms of data management and getting your data ready for analysis. We have a few minutes for questions if we want to talk about anything that we discussed.
I'm gonna ask a random question. Have you ever encountered a case where like a respondent couldn't be linked to a tract? Has that become an issue yet?
Yeah, so definitely depending on your contextual data. So if you are using data that kind of covers the entirety of the United States, that's a little less likely because you're going to have contextual data for every census tract in the United States. But if you're using contextual data that is maybe limited in terms of the number of states or the number of census tracts or counties, then yeah, you'll have individual level data that you have their census tract identification, but that census tract is not represented in that contextual data. So that might come across a lot of times, like with Mateo's presentation with historical level data, right? I've used the historic redlining scores data, and that there was only a certain type of census tract that was redlined, and so we don't have HRS respondents that are living in all of we have HRS respondents that are living in the redline census tracts, but we have HRS respondents that are living in census tracts that were not redlined, right? And so that's an instance where that occurs for sure.
Can you give the example?
Oh yeah, and then you also have Puerto Rico, where you have people, maybe if you have contextual data that doesn't cover Puerto Rico and people are living in Puerto Rico, you're not going to get a merge there, the individual levels, and vice versa if you don't have people from your individual data set in Puerto Rico.
So I have a few questions. One is, based on my understanding, we don't need to merge, at least with HRS data ourselves. If we get access to the enclave, we would have access to the merged data with the CDR information, or that is not the case. We will do the merge based on the geographic area that we want ourselves.
Yeah, you will do the merge based off the geographic area. So you'll just be provided the CDR data as well as the geographic detail file and the other HRS data products as well.
Okay, perfect. So the second question is, between cross-sectional, it's clearer. For longitudinal, let's say I am using 2010 to 2020 data, just an arbitrary example.
Yeah.
Assuming that these geographic information change over time, should I use should I use the last year available of CRD, or should I do it for each year separately based on the addresses that I have for that year? You see what I'm saying, in a cross-sectional manner, and then pull it together.
So because we harmonized the census tracts to the 2010 census tract boundaries in the CDR, that means that even though an individual's census tract might change from year to year, they might move. When they make that move, we're still locking them to the 2010 boundaries of that census tract.
I see.
Right? So even if they move to a census tract in 2015 that wasn't there in 2010, we are using that census tract value for 2010. That's not a great explanation.
So originally, the idea was to provide linked data, because David Weir thought that would be the easiest thing for users to do. And then when Jessica Fall and I started trying to actually do it, I think we started with the Dartmouth Atlas of hair data, which was a part of the problem. It was too much, because you have tens of thousands of HRS respondents that have now potentially been in the survey for 2 to 3 decades worth of waves. So when we tried to merge into the respondent level, we realized that the data file was it was not something that people would be able to work with. So what we decided, and rather than me making many choices to limit the data set, we decided to provide the complete data set, and the user would go through and extract what they wanted out of the data set. This is why we're going to provide some worksheets to help people do the merge once you get in there. The other thing we have, which I think I've done this in a presentation, but I couldn't find it, but I have tried to show people a stylized version of what the data look like when you actually get in there, which of course I can't show people the census tract, so I made up numbers. But the way it's formatted right now is HRS has their files in a long format. So it's a person ID and a year, all the way down as many years as they've been in the study.
Okay.
But then in each column, you have these linking variables like link send 2010. Okay. You have it all the way down the column. So every respondent at every survey wave is linked to their 2010 census tract geography.
But that's my question. This 2010 data has changed. Do you think would that create some false information if people move, because we are bounding them to their 2010 geographic location?
All we've done is we've taken all of the geography over time and standardized it by the 2010 geography.
I see.
That only impacts the CDR measures. It doesn't impact the respondents. So they can move around. It's just wherever their tract is, we're always standardizing it to this 2010 year so that all of the data can be merged in, and you don't have to worry about whether or not a census tract value in your 2010 data is being assigned to a tract that actually had different values in 2000. So we've taken all of that on for people, so you don't have to worry about it. So people can move around in the HRS.
Okay,
This was just a way to account for these issues where census tracts break out into multiple census tracts. This happens every 10 years. But there are files that other researchers produce and the census as well that help us account for all of those changes over time. And so everything is put into 2010 geography. So that also means like if a user wants to bring data into the enclave, as long as it's in 2010 geography, they can do it. But actually HRS updated with 2020 geography. So at some point we might take all of our boundaries and regularize them to 2020 boundaries. We'll
Okay.
probably start doing that soon. But that means that you can use the data without worrying about boundary changes because we've taken care of all of that for census tracts and for counties.
okay.
We haven't done anything so lower than that. You don't have to worry as much. Like blocks come and go, but they don't change boundaries. And we don't deal with some of the other boundary changes, but I think those are less common. People don't. It's not as much of an issue. It's really census tract boundary changes happen a lot every 10 years, and county boundary changes happen, 4 or 5 of them change at least every 10 years, probably.
Thank you. And last question, you mentioned if we want to match on the geographic unit, start with the largest unit, state, am I correct? Then county, then probably census tract. Okay.
I mean, if you're comfortable with your data, you don't necessarily have to do that. We just find that's the best way to kind of like make sure that if we have 2 geographic data sets at the census tract level, we can go ahead and match those together and we can see really clearly, okay, we still have, a match of 72,000 census tracts, right?
It makes it easier to control it.
Yes,
If
exactly.
we don't do that, it will match for everything.
Yeah, it'll match on, so say you have a longitudinal data set, it'll match on all of your observations from 2010 to 2020 for all of your respondents. And so now you're working with like 100,000 to, 100,000 observations or something like that. And it's much less clear if they're not matching because you don't have their census tract. Are they not matching because they're not represented in the geographic data? Are they not matching because you did something as the coder, right? It's a little bit more unclear about why you might have discrepancies in your list.
Okay, can I ask one last, two questions, sorry. So how would you change the command if you want to just do it based on the state or just do it based on the county? Would you use a different command to do that, going the step by step?
So you would use the same, as long as your state FIPS code uniquely identifies observations in your geographic data set or in your contextual data set, you would use the same command. So here, link send 2010 would just be the state FIPS code instead. And here
just the 2-digit then.
yeah, just the 2-digit, and it would still be the same. Here we're starting with the geographic data. So the geographic data, the state would be a unique identifier.
Got it.
In the HRS data, the state would not be a unique identifier, right? Because you have multiple respondents in the same state. And so that's why we use a one-to-many merge here.
And if I wanted to do it, for instance, at the county level, then I would leave the FIPS code at 5-digit and then, okay, got it, thank you.
Yeah.
One last question. I'm using a lot of, I know this is developed for HRS, but if we use, I work with claims data a lot.
Okay.
And I'm assuming this CDR data, like I'm merging claims data with ARF data or NANDA data, I should be able to do the same using this FIPS code to merge it with claims data.
Yeah, if you're using, so in this case, I just had HRS because that's what we use a lot. That's an individual level data. But if you have another data set at, for claims, maybe it's not at an individual level, it's at an insurance level or something like that. Then this could be a totally different data set here.
No, but your claims data is at the individual level. So each HRS respondent got linked to all of their CMS records. So you have, now you're doing a different linking identifier, but that's what we do. You linked this to biological age, Unyang linked to the clocks. So basically you take the HRS respondent data and you can do a regular merge on that. That's just a one-to-one merge because you're merging the respondent CMS records on their own HHIDPN variable, which is HRS's identifier.
Yeah.
So that's a separate merge. That's I actually don't know if this has to be a one-to-many merge either. But I think you would probably merge your geographic data with your respondents, and you could then just bring your CMS, or you'd probably merge your CMS data in first. It's not really CMS data though, it's the individual HRS records linked to their.
No, my question was totally different, like, forget about HRS and the link between HRS and fee-for-service claims data. If I just use claims data and I have the.
For an
zip code-
individual or at the area level?
No, at the individual level,
Yeah, so you have an individual characteristic, which is all of their,
yes. And I have their zip code.
and you have their zip code,
11-digit.
and you need to merge it on zip code.
Yes, yeah.
Yeah, and we actually haven't produced a lot of zip code files, but we have more and more people asking for
Yeah.
claims linkages. And I work in the Schaefer Center here with a lot of health economists that work with claims. So we're planning to work with them to try to create more CMS linkable files, because people come to us sometimes, but we haven't created, like with those raster files that we have, we aggregate them up to census tract geography, not to zip codes necessarily. So we need to do
Yes.
that for the people who work in CMS.
Okay. Thank you.
And I just also want to mention this link send 2010, that's an identifier that HRS uses for census tracts. But they use different identifiers for states and counties, so you always have to make sure whatever data set you're working in, you check to see what the common geographic identifiers are, and then you need to change the variables usually in an extra step to make sure that you can do the linkage. And also in a data set like this, where you could have people at different years, you could have pollution or temperature at different years, you have to actually be a little bit thoughtful about how you're doing your merge and what you want that data frame to look like for your analyses. So we don't have a lot of examples about that because it's highly specific. The merge is going to be highly specific to your research goal. But you should think about, this is geographic data over time that's being linked in many of these surveys to individuals over time. And so you want to think about, you're actually often going to be linking maybe on geography plus year, not just geography. And that's a more complex merge.
Each year. All right, so now we'll move forward to data visualization.
Hey, I'll use mic because my voice is not that loud, so let me use this. All right. Okay, so I want to emphasize that you should always visualize your geographic data first. And there are two types of visualization that you can do. First, you can do the visualization prior to merging your contextual data source to the individual level data set to just understand contextual data sets better. And that includes examination of the spatial temporal distributions and then the range of the values, which I will show in a minute. And then second, after merging, you also have to do the visualization to look at how your sample distribution varies for contextual data vary. For example, individual level sample that you have may have different distribution than the entire United States that contextual data source represents. And especially when you're interested in the stratified analysis by special groups, like by gender or race ethnicity, you should make sure that your sample has sufficient variation across different levels of environmental stressors. And then I also want to emphasize that you should also check the data specific roles and requirements. So for here, I brought the HRS example, and then it clearly mentioned that you should not make maps, scatter plots, or graphs that allow geographic geospatial data to be identified or that show any geographic area below the census division level. Census division level is huge, right? So you cannot make a map below the census division level, even at the state level. So to make sure that do not map the location of the HRS sample under the census division level once you merge your contextual level data to the individual level data sets. I will skip this part. This is just me explaining how to make your graph a little bit prettier in Stata. So you can use different schemes online, which will make you make prettier graph than the default Stata schemes. Okay, so first I want to talk about the use the box plot to identify outliers. Here you see that I provide a very brief data code, but we'll provide the actual data code after the workshop, so don't worry. So here this shows the PM2.5 values across the year in the United Census tracts. So you can see that first, the median value of PM2.5 has been decreasing as we learned the yesterday's workshop. And then you can also see that there are a lot of variation even in the outliers. And why this is important? Because that will inform you how you want to code your variables or the how you want to examine or expectation about the variation of PM2.5 once you link to the contextual level data to your individual level data sets. And another box plot shows now the monthly variation of PM2.5 in 2016 at the US using the US Census tracts. And then you can see that there are some variation, right? We can see in general there is huge outlier values, particularly happening in winter season, January, February, November, and December. And this can inform your decision around how you want to make contextual level variable in your sample. You can use the annual average value of PM2.5. But if you can see there's a great outliers in the happening in the winter year, you may want to make a monthly average value or even a winter specific average value of PM2.5, depending on your research questions. And then another graph that I want to introduce is use the histogram to understand the distribution better. And this shows the histogram of average PM2.5 using the 1 year average value prior to the 2016. And we can see that the average value is about 8.5 or so. But if you graph the temporal variation, if you graph the different time frame average value of PM2.5, you will see the different patterns here. If you use the 10-year average values of PM2.5 using the data from 2006 to 2016, you can now see that the median is a little bit higher compared to if you just use the 1 year average value. So again, this will inform your decision around how you want to treat your contextual level variable. And this is another graph you can use to understand the time trends of your variable better. So I will walk through this graph a little bit more detail. So y-axis represents the number of extreme heat days, and then x-axis shows different years, right? And then each gray dots here, it shows the state mean. So each year have I guess 49 states because that's the data availability. And then the red dot here represents now the national mean. So if you use draw the smooth line over there, you can see that it's generally increasing over time. And then the reason why I draw this graph is also to understand what's happening for my study period. So I use this HRS from 2006 and 2018 for this project. And then you can see that, for my study period, there has been really increasing trends of number of extreme heat days. So that's another way that you can use kind of time trends plots to better understand just background of what's happening. And this is just step by step how to create this graph in Stata. And finally, you can use map. You can make map even using Excel. I found out pretty recently from Jennifer and Kelly, and I was very amazed because I always use like Stata or R and then like different codes, but this is really like just a way to quickly make a map and produce publishable graphs. Oops, the map is not showing here. That's strange. Oh, there you go. All right, so you can just open your Excel and then start by exporting your data into Excel spreadsheet. And here we use this data geography. And then in the y-axis, you can, on the y column, you can just import your data to be mapped. But important thing to remember is for the geography, you should use the state or county names, not the actual zip codes, because we realize that Excel wouldn't recognize zip codes as a geography level. So just type the name of whatever geography you want to use, and then values. And then if you highlight the cells with your geography and then in the data tab, you can locate the data types and there is geography icon there. So if you click the geography icon, and then finally you can highlight the cells with your geography. And then if you go to the insert tab and select the field map, and that's it. That just produced map like this. So you can try out with different geography. I tried like South Korea and it produced beautiful graphs. So you can try whatever you want to do. So, but then we realized that Excel usually works better for this like the country, like state, like large scale geography better. But if you wanted to more, if you want to get map at more granular level, now you can use Stata or R, but I want to introduce Stata here. So this map shows the 2016 county level model counts. And important thing to remember to produce a map, you should use the shape files, which refer to the digital representation of geographic features that is necessary to create maps, especially in Stata. And I'm gonna introduce two different types of shape file that you can use. So first one is the title line shape files, which are the extracts of selected geography from the census Bruno master address file or title system. So I inserted link here. You can just go to the link and then download the title files. And then the actual code to like load the shape files into the data and create the map, we're gonna provide that after the workshop because it's kind of long codes. And I wanna get into detail about that, but that's one way to create map in Stata. But you can also use different shape files to produce map in Stata. So this now shows 2016 county level heat days at the extreme caution level. And there is another shape file called carpool graphic boundary files, which are simplified representation of selected geographic area. So if you compare both, you can see that if I use the title file as it is, it wouldn't exclude the lake and the Mishnah. But then if I use a cartographic file, then it actually actually exclude the lake area so that it kind of resemble more realistic maps of the United States. So this is just another example. The left-hand side is the actual representation of the Michigan, and then if I use title file, is the official areas of county, including water area. So that's why it produced kind of unfamiliar look as we expect. but the cartographic boundary shows different representation. And cartographic boundary files comes in 3 different types. So if you can see that if you use more like granular scale, you would get more like detailed the map files, but if you go to the more larger values here, you would get the more generalized and simplified version. So that's another thing. And then finally, you can use R to create a map. So there is a map view R package, which I found fascinating. It can produce some geographic data, even interactive and zoomable. Introduce that, but remember that data needs to be a spatial object, which is stored as a tabular format with a spatial column that includes. If you see the geometry column, it actually has to have x and y coordinates. So this is like a prerequisite to produce to use the map view in the R. And then the actual code is pretty simple. Then you can make the that prettier. So I wanna show the actual. Oh, yeah, there you go. Okay, so if you create map using the map view package, you have like different background map, which is pretty cool. And then if you like go to here, so here it shows the percentage of non-Hispanic whites. And as you can see here, in the Los Angeles, we can see that like Beverly Hills, there is like a lot of non-Hispanic white proportion, but if you look at some of the downtown areas, it now has a lot of Asian population. Probably this is Koreatown, I assume. So cool thing about this map view package is it shows not only the selected variable that you have, but also show different variables that you have in your data set. So you can kind of compare what's shown in the map, but also another data elements that in your data set. So this is pretty cool command that you can use. Oops.
That's an R package?
Mhm.
That's interactive?
And I found that, so I actually learned it by myself using the online resource available there. So I highly recommend to use those links to learn, like teach yourself about how to create. Okay, and there are another program options that you can use, which is ArcGIS and QGIS. This is like click and point program, and then you can make more sophisticated map if you want. But one thing to point out is ArcGIS you have to pay, and then QGIS is free version of more sophisticated program. And finally, let's suppose that you merge your contextual data with your HRS sample. And now this represents the distribution of PM2.5 happening in the HRS sample. And so you can compare the distributions of the contextual PM2.5 here, the distribution of PM2.5 in your data set with the distribution of it across the United States. And it kind of resemble, but it's also slightly different. So you may want to understand whether your sample is, your sample may not be representative of United States, and you wanted to take that account when you approach to your research question. Finally, especially when you have question around the health disparity, you may want to do the group-based analysis. And then one thing to make sure is to you have enough variation or enough sample sizes to do so. So what's happening in this graph is on the y-axis, you have mean daily minimum temperature in cold season. And then on the y-axis, you have daily maximum temperature in the warm season. And then this gray vertical and the horizontal bar represent the medium value. So that we have 4 different kind of geographic climate condition happening. And then you can see that there are concentration, although like on the bottom, the diagonal two area are having more concentration of the people, but also we do see people in the all like 4 elements of climate environments. And then another important thing is it also have decent concentration of all racial ethnic groups so that we can like ensure that our findings are not just about black living in a certain area or white living in a certain area. We actually have like enough power to compare similar or different similarity and differences across the different environments or groups. So that's it.
Okay, so we will finish off with some comments on estimating these types of models with contextual and individual level data. All right. So one of the first things that's helpful that kind of goes along with where Eun-Young left off is that when you have nested data, you always want to go ahead and check for clustering in your data. Sometimes this doesn't make it to write your actual like method section or the research paper, but it's helpful as the researcher to know if you have clustering happening in your data and to what extent. And so this example that I'm providing here from this data code is from a 3-level model. So I have people, observations nested in people, and people nested in census tracts, right? Obviously, if you were in just a 2-level format where you had people nested in census tract, this code gets simplified a bit. You don't need as many lines of code here or to create as many variables. But as Eun-Young said, we're going to send you, as much information as we have. So this first kind of block of code is providing information at the kind of person year level. And so we're thinking about how many waves of data that we might have. So in this case, we have 11 waves of data and the average number of waves in our sample. We can also calculate information on the average first year of an observation in our sample. So we have kind of the typical observation coming in around 2000, and then the last year being 2014. And then what is probably most useful for the contextual data sets is this last variable here, this track count variable, which tells us how many observations are in our census tracts. And so this just provides some summary information. Where the typical, we have about 83 on average observations within a census tract in this example. That variable is being produced by this last line of code here. If you were in a 2-level format, you would be able to just adjust this code with the respondent ID rather than the person year identifier. And so then you can use that information to just, that track count variable to just visual representation of the distribution of observations across census tracts. You could also create some frequency tables or something like that to check for that clustering. Another way, this isn't really like clustering in the true sense, but this also goes along with some of Eun-Young's visualizations. So you also probably want to check for clustering or groupings across your contextual variable. A lot of times we're bringing in our contextual data set because we have kind of a key independent variable from that contextual data. And so it's helpful to know if you even have variation from the onset of your contextual variable across your outcome. And so you can create, obviously, more graphs. The code for this is similar to the code that Nunyan presented, and this is showing us the mean distribution of cognitive functioning scores by that historic redlining indicator of census tracts. Just hide these. And so that's just like a quick bivariate check to see, okay, is this contextual variable working in the way that I'm expecting it to work in my models, right? And then we can do a more formal test for clustering. And so if you're familiar with multi-level models, then you're probably familiar with what's called the interclass correlation coefficient. We can calculate an ICC in our data and in our model, and we can use that information to justify whether we want to move forward in a multi-level format, or if we want to go for a more parsimonious model with a single level regression. And so we can calculate the ICC off of what we call an unconditional model, where you're predicting your outcome variable without any predictors in the model. Here in Stata, again, I'm in that 3-level format, longitudinal format. So I'm including a random intercept for my tract, and then I'm also including a random intercept for my person ID. And then on line 35, I'm asking Stata to provide me with that ICC calculation. And so that produces an output that might look something like this. Again, I'm in a 3-level format, so I'm getting multiple ICCs because I have nesting happening track level and the person level. If you were in a 2-level format, you would just get one ICC here in the output. And so here we can see for the census tract that this 6.16 is telling us that about 17% of our variation on cognitive functioning, which is our outcome measure, can be attributable to variation at the census tract level. So there's no really hard or fast rules when it comes to the value, like a cutoff value of the ICC that you're looking for. If the ICC is like 0, right, you have no variation happening at your geographic level or contextual level, then that can be justification for just simply moving into a single level format. You don't need to add complications to your model by being in a multi-level framework. If your ICC is quite high, that's a reason to stick with a multi-level model. Also, as you're thinking about making decisions about which model is appropriate to run, you also want to think about how you're handling your population weights that are in your individual level data set. This is particularly true if you're having that longitudinal framework. So you want to make decisions about whether you are using a baseline weight. Some people use the weight from the final year in the survey. Other people use the yearly weight that changes with the person as they have multiple observations. All of those decisions are going to matter for the computational power needed to run these types of multi-level models. You'll notice in this example here, I have this population weight of sample weight 1,000. That might look a little different than your survey weights you're used to using in your data sets. And that is what we call foreshadowing. So we're going to talk about that in a couple slides. And that's also what we call a joke. Okay, so say you're good to go with a single level model. You have a low ICC, there's no real need for you to move into that multi-level model framework. You still have nested data, right? You still are going to have people nested in census tracts, people nested in counties. And so you still want to adjust for that nesting in your modeling. And so we can do this in Stata by calculating robust standard errors and using this VCE cluster adjustment following our regression command. And so here I'm adjusting for clustering at the census tract level. And then in my output, it's telling me, yep, I've adjusted for about 10,000 census tracts. And then I'm giving you the robust standard errors for your beta coefficients. If you are in a longitudinal framework and you have 2 sets of nesting, right, you might want to be adjusting these standard errors for multiple levels, the census tract and the person. Fortunately, this VCE options data doesn't let you include multiple variables in that command line. However, there are some user written commands that do. And so I've been using this VCEMWay command. There are others out there if you kind of just Google around, or if you're on the Statalist website or something like that. And so this command allows you to run that exact same regression, and now including in your cluster adjustment the nesting at the person level and the nesting at the census tract level. And so here you can see the output looks a little bit different. Mostly you get this note at the end here that tells you about the clustering and the number of groups you have at each level. And you can see, so from our one level adjustment for this declining group here, we had about a standard error of 0.2662. That is roughly the same when we move to this two level adjustment at the single level. It changes at about like fourth or fifth decimal point, but we can see that we're having kind of comparable results in our standard errors. And then, of course, if you do decide to move to the multi-level framework instead, then you're including those random intercepts at the geographic level and at the person level if you're longitudinal. And then you can see, again, we have those robust standard errors being calculated. And now that standard error looks a lot different, not a lot different, but looks different compared to those single level adjustments, right? All right, so back to that weight variable. Something that we have run into a lot when using the CDR data, especially when we're in three-level models, is that we have some convergence issues that happen. So our models run and run and run and run, and you go get a coffee and you come back and they're still running, right? And so for us, a lot of times the reason for that convergence is because on the population weight variable, we have outliers. So here's just a box plot of a sampling weight variable. You can see the number of outliers here. And so that can be a challenge, especially for programs like Stata and R. Those programs, you know, they're not necessarily built to run multi-level models, you know, by themselves. They're useful for a bunch of different things. And so these can just be a challenge computationally. And so one of the solutions that we tend to use is to rescale the weights. So you can typically rescale weights in two ways. So one is that you actually just divide the sampling weight by a certain number. So here in this code, I'm dividing by different iterations of 10, 100, 1,000, 10,000. Another really common way that you rescale weights is to take the mean value of the weight and to divide the sampling weight by the mean. Another thing you can do is you can trim your weights. So in this code here, I am just top coding the sampling weight variable at the 95th percentile. You could also do the 90th percentile or something like that depending on how many outliers you have. You can also do a combination, right? You can scale and trim your weights. I ran into a situation where I had major convergence issues. I had a very delicate modeling structure. And so I was doing a lot of scaling and trimming. And so when you do run into this problem and you try to scale your weights as a solution, it is really important that you're constantly checking in with your models about how these scaled or trimmed weights are potentially affecting your results, not only from a convergence standpoint. So here you can see I ran a couple different weighting schemes and just was checking to see how many models I had that were converging or not converging. But you also want to be checking your standard errors, your coefficients when you choose these different scaling procedures, because you want to make sure you're not introducing bias into your estimations by making these decisions, right? And so this solution is not quick, right? You are running your models again, scaling again, running your models again, scaling again, checking across a bunch of different models. This is just a very small snippet of a large Excel workbook that I had comparing across my different modeling frames. And you can see here, I was also checking as well with different ways of assigning that population weight variable, whether I used the yearly weight or the weight from the last year in the survey. And then finally, if nothing else works and you're just not getting that model to converge, you're getting out of Stata, right? And you're getting out of R. You're going to move into a software that's designed for these types of multi-level models. It's just going to give you much more power to be able to estimate your models. That could be N plus or an HLM, like that. That is another note that we haven't talked about yet. I think that it is, if you're kind of just sort of starting these CDR projects, they can be a lot for your devices, right? Your laptops, your computers. And so, it's really helpful to make sure that you have the right tech to run some of these models. It's just going to make your life a lot easier. So making sure you have, the higher flavors of Stata, making sure you have the right processing power on your machine. That can all help speed up some of these processes. When I was running these different weighting schemes, I was working on Stata SE, which is not the most advanced of the Statas, and it would take me, I had about 15 models. It would take maybe like 4 or 5 hours to run through my models, right? And so that's tough when you're just trying to check. I just made one adjustment. I just want to check what the outcome looks like, right? That can take a week or so of work to just make sure that you're scaling your weight correctly, right?
So the first presentation is going to be by one of my PhD students, Rachel Wilkie. So Rachel's in our Population Health and Place program. And she's actually finishing her PhD this year, and she just found out yesterday that she's gotten a postdoctoral position. Again, if you have any trouble hearing over in the back corner, she can use the microphone here. But she's going to talk about neighborhood SES measures. We're kind of going from like the easiest measurement construction to some of the more complex constructions that require a bit more understanding of programs and some spatial approaches.
Okay. Does this work? Okay. I'll try to use this because I'm not sure how loud my voice is. So yes, I'm Rachel. I'm a PhD candidate in the Population Health and Place program. This is a short presentation about constructing and using neighborhood SES measures. So I'm going to go over 4 different approaches to measuring neighborhood socioeconomic status, mostly focusing on deprivation, but as we'll see in the third slide, the third section, we'll look at affluence as well. So starting from the most simple way to measure neighborhood socioeconomic status, down to the more complicated way. Okay, so first of all, we'll start with single indicator socioeconomic measures. So these things could be measures like poverty status, unemployment. These are usually simple to measure and interpret because they're only one single indicator. But they don't take into consideration other aspects of socioeconomic status or deprivation, which could be relevant to the overall context of that area. There's also potential issues with skewed distributions of using a single indicator, which there are ways to get rid of that as well. So I'm using the example of poverty. So you can see on the histogram on the left here, the poverty variable is very skewed. With there's never going to be 100% poverty in one neighborhood. And so most neighborhoods are more like 10%. I think that's around the median, 10 or 12%. And then they go up, get more and more infrequent to have a much higher percentage of poverty. So how I got around this was to create quintiles of poverty in Los Angeles County. So actually the quintiles are for the whole US, and I just mapped them. So you can see that here the more this is like downtown and South LA are high concentrations of poverty, and also some of these rural areas also high poverty. And by poverty, I'm talking about the percentage of the population below 50% of the median income. In terms of thinking about more using multiple indicators to create a measure, we can think about the theory behind deprivation or socioeconomic status and select indicators which measure these different dimensions. So things like income, social class, education, employment, housing. And then in order to create an index, we can standardize each of these indicators and then sum them together. And for this, we can choose to weight everything the same. So we might say, okay, we think income, education, and employment are this important. So that's just sum them together equally. Or we might say, okay, I think education is the most important indicator, so I'm going to give that a higher weight than the other variables. And because these are quite simple, we can replicate and compare these indicators across time and space. So we might be able to construct similar measures in different countries, in different census years, but they also don't measure more complex aspects of deprivation. They don't give the full picture. So I mapped here the Townsend index, and this is a composite measure of area level deprivation, which was developed in Britain by Peter Townsend in 1988. So it's a very long established measure, and it's been validated and found to be associated with adverse outcomes in Britain, and other people have used it in other countries as well. It is very simple, only uses 4 indicators. Firstly, unemployment, secondly, home ownership and crowding and vehicle access. So I replicated this index using American Community Survey data from 2014 to 2018. The variables are in this table here. And I have, again, made quintiles of the variable and mapped them in Los Angeles County. So already you can see that the distribution of deprivation is different to the distribution of poverty. And at the end, I'll show all of the maps together so you can compare. So you can also see here the more South LA is again got high deprivation. So the third way that we can make socioeconomic measures is using data-driven methods. And this uses statistical methods to combine variables into summary measures. So different approaches that you could choose would be factor analysis, principal components analysis, and logistic regression. However, we still need to think about the theory behind the socioeconomic status of the neighborhood when we think about which indicators to include. And each indicator is given a data-driven weighting. So the importance of indicator in the measure is determined by the data methods. And because of this, it's more difficult to replicate across time and space because as data changes over time, the weightings would change over time. So these are the 9 variables indicators in ACS that I selected to create 2 summary measures using factor analysis. So this is just a correlation plot showing that, as you may expect, things like having no high school degree, being unemployed, having public assistance income, or being in poverty are all correlated together. And also being a homeowner or college graduate or having a management or professional job. These are also quite correlated as well. So this, so I ran a factor analysis on these variables. So these are all percentage variables of the population or percentage of households. And the screen plot basically just shows the individual factors that the factor analysis found. So we selected the first 2 factors based on their how important they were. And then these are the rotated factor loadings. So we can see that these more affluent variables like college graduation or management professional occupations, median house value and house income, these are all have very high loadings. So then the low or negative loadings are things like unemployment or less than high school education. So we can conceptualize this a bit as affluence. So we give it a name. And then on the second one, we call it deprivation because this is kind of not quite the opposite, but very high loadings on the more variables associated with deprivation and negative loadings on the variables associated with affluence. So I have mapped both of these. In green, we have affluence. So the darkest blue is the highest affluence. So areas like Malibu along the coast. And then in the pink, again, I mapped deprivation quintiles. And we also, again, have this South LA area, which is highly deprived. But also it's a little bit different than the previous map. And our final method of creating indices of deprivation is this really complicated multi-dimensional indices. These use a large number of indicators from multiple data sources, such as the census data, environmental data, and health data. And these are, so each dimension of deprivation will have several indicators that create a domain score. And these are often published by governments of several countries. So England, Scotland, Northern Ireland, New Zealand have them, among other countries. Unfortunately, there's no widely accepted framework for creating these or for choosing the weights or combining indicators, and this could be data-driven or theory-driven. And because of this, it's quite difficult to replicate or compare across countries for long time periods, because the indicators that go into the index are different depending on the country, depending on the time. So this is an example. So the US does not have one of these, but this is the Scottish Index of Multiple Deprivation, and you can see there are 7 overall domains, and then these are the items that are included in each one, and the methods used to aggregate them and create scores, and then the weightings. So these two, employment and income, are weighted the highest, say 12 each, and then housing is weighted the lowest, only 1. So there are a lot of challenges with creating these because of the amount of data that it involves, and most of the data that is included in the Scottish Index is not published or available to the public. So most of it is government data that they collect themselves and they aggregate into this index. So especially for small areas, you can't really publish a lot of this data to be visible to everybody, but what they can do is they can put it all together and publish this index of deprivation. And it's used in a lot of studies of health and life expectancy and shows really strong associations with inequalities basically in health. The last thing I want to talk about is this validation and uncertainty of indices, deprivation, or socioeconomic status. I think it's really important to think about validation, especially if you're just putting variables together. You know, you might think that you're measuring something like deprivation, but you need to check this against other data and against your outcomes to be sure that you're using a valid measure and that there might not be any other measures which are more relevant or better to use. So ways you can check that your index is valid or your measure is valid is by checking the correlations. So you want to see, are these indicators associated with one another? Is my index associated with other deprivation measures? Is there an association between my measure and health outcomes that I'm interested in or other health outcomes? So you could use life expectancy measures, which are often published at the small area level. Or if you have linked data like to HRS, you can look at inequalities in health in those samples. And also we want to think about, is this measure working equally well across different contexts and subpopulations? So does this measure work in rural areas and urban areas in the same way? Or does this measure also work in ethnic enclaves or other unique demographic areas? Finally, the last thing is reducing uncertainty. And for some very small areas with low populations, there might be uncertainty in the measures. So for example, the American Community Survey publishes the confidence intervals or the margin of error, of each indicator. And one way to reduce uncertainty is using shrinkage estimation, which uses the values of the surrounding tracts or neighborhoods to kind of influence the measurement and reduce uncertainty. Another approach, which is what I use, is using categorical measures such as quintiles or deciles of called deprivation. And it's a very common approach which is used in lots of different things. Yeah, and these are the final formats again, just to show a quick comparison, but you know, these two are fairly similar, but they're quite different to the quality map. And that is all that I have today. Anyone got any questions?
Question. So, how to validate an index? So you mentioned a few methods that's the correlation between your index and other areas. How can which one is better?
So in terms of, so I would look at like a correlation plot, like what the one that I showed earlier. Thinking about, so if these are the indicators I want to use in my index, and I can do that. If there's another index that I'm thinking which one is better, then I could check both. And then I would also maybe check both in models and see, well, which one is showing the highest inequalities. This one is the one that has the highest inequalities is probably the more effective in the index. Does that make sense?
So how do you know you have the higher quality? Is there any statistic? For example, R-square, AUC, something.
I think from what I've done is mostly just being qualitative, like looking at the correlation plots and seeing which ones have higher correlations, or looking at models and seeing which ones have the higher associations. But it's a qualitative decision. You know, there probably are ways to.
I was gonna say, like, there's AUC or WAF curve, so you can test for the specificity of that specific indice on like an outcome, and you can see it'll tell you statistically like if it's performing better, if it's like capturing, like what you're actually looking for.
So I think another way you might consider to do validation is to find an established kind of deprivation measures and use that as your like a landmark and compare with the congruity of image with your like constructed index. I think that can another way to create a new like a comparison group kind of thing. Yeah.
And sometimes there might not be a standard published index as well.
There's a lot of them too. Like there's like the area deprivation index, neighborhood deprivation index, investors index, like
Yeah, I mean, this is actually what Rachel has done. She didn't create these. These are based on established indices. For the factor analytic approach, that's just a way to try to reduce the dimensionality of a lot of variables. Actually, we ended up with affluence and disadvantage factors that I worked with when I was a graduate student working only on data from the city of Chicago. But affluence and disadvantage, they're theory-based. So we don't compare model fit. Like we go with whatever measures theoretically most the best fit for our hypothesis testing.
So question on a good measure or indicator for multidimensional poverty in low-income countries.
I don't know.
Yeah, so it's really variable because it depends on what data the countries publish. And as far as I know, there's no standard data that's published, especially at small area levels. So you really have to rely on what is there and what is available. And in terms of doing deprivation across states, so I have one of my dissertation papers looks at deprivation and life expectancy at the tract level, but I also do a state comparison. And for that, I used one deprivation index for the whole United States, but I calculated the quintiles within states. So the quintile variable was dependent on the state for my between state analysis.
Okay, thank you so much, Rachel.
thank you.
Okay, so our next speaker is Catherine Garcia. She's an assistant professor at Syracuse University. I invited her to this workshop because she's been doing some very interesting work on creating instead of a continuous summary measure, which is essentially a type of a mean, she's actually taking a categorical approach and using latent class analysis. And she's been doing this in Puerto Rico, which is, I don't think we actually know much about neighborhoods and aging in Puerto Rico. So she's doing very new work. So this is going to be in the Puerto Rican context, but I think her methodological approach can be extended to a lot of others.
Oh, doesn't matter.
You can leave this one sitting here if you want. This is for the Zoom people. So
Oh,
I
I
want to
see.
make sure that they hear you.
Okay.
Everybody's-
So actually, I'm really glad Rachel talked about these factor analysis. I was touching on it a little bit. So let's get into this. Yeah. So I had to do this in the PDF form just for the purposes of this presentation, but I am going to upload this to my GitHub, which is going to have more interactive and dynamic ways to interact with the presentation. But all of the hyperlinks do work. So like if you wanted to visit my website, you can click on that. My Twitter's here and my GitHub is right here. All right, so as we know, this whole workshop would be possible thanks to everything that Jennifer and the USC team has done to make this possible. But I also want to take some time and thank all of you for being here, right? Because taxpayer money is being invested in y'all in this session, so we gotta do as we can, with what we're learning here, and take it to make communities, better, and give them better opportunities for healthy aging. So I want to thank y'all here for being here in this space and sharing it and for showing up. And hopefully what they're learning here, you'll do some good with that. All right. So given that I do not have an hour, 2 hours to talk about all of this, it's going to be basically a really quick introduction into some latent variable modeling and going through a quick illustration of how you can use latent cost analysis or latent profile analysis to classify neighborhoods, which I'm going to do in the Puerto Rican context. So here's an outline for those who like that for navigation purposes. All right, so before I get into this, has anyone here taken a structural equation modeling or any type of latent variable modeling course, workshop, or whatever? Raise your hand. Awesome, that's a lot of you in this room, but even if you have not, it does not mean that you will not benefit from hearing about this. So I will talk a little bit quickly about some of these latent variable measurement models. So for those who have not taken an SEM course, basically latent variables are essentially variables, categorical variables that are not measured directly, but we're using observed variables to actually capture that latent construct, right? So like Rachel was talking about, some of these neighborhood indices under that factor analysis, framework. But FA and also latent cost analysis, also known as LCA. So these actually are considered latent variable measurement models. Okay, so they're in the same wheelhouse, and they're being used, not just by people like me or people in this room, but it's being used by a bunch of researchers to capture these latent constructs or classes that do represent various aspects of neighborhoods. So, FA and LCA are both valuable tools. I don't want y'all to sit here and think that, LCA is better than FA, right? Or FA is better than LCA. There's just two different approaches depending on your research question and what your objectives are and what you could potentially use to actually assess some of the heterogeneity that is associated with neighborhoods, right? So I just want y'all to make sure that this is not a either or conversation. So you can use these methods to, either develop more comprehensive or nuanced measures that can reflect various underlying structures or classes within neighborhoods, which can also help us to better understand how, these various determinants, in neighborhoods, do contribute to overall health and well-being across, contexts. All right, so factor analysis, as we kind of heard a little bit from Rachel's and a little bit that Jennifer did mention. So this is a variable reduction format, right? So people tend to use FA to identify underlying factors or even latent constructs that do explain observed variation in a set of variables, right? So I have some notes here about creating composite indices, which, we've seen a lot in the neighborhoods literature. But the point is that, we can use FA to understand multidimensional constructs in neighborhoods because we know that things are always co-occurring, right? Like nothing is just standing by itself. LCA or latent cost analysis is similar, but it's a little bit different than FA, right? So with latent cost analysis, you actually want to identify homogeneous groups. So depending, we'll get into this with the example, but you actually want to try to find, a certain number of classes or groups within whatever population that you're studying to get, a certain patterns that, are in your variables, and that will describe, different groups of the population, and they're mutually exclusive. And one thing that I do appreciate about latent class analysis is that it really gives you the opportunity to examine heterogeneity within neighborhoods, which sometimes can get lost when you're creating indices, right? So you may not get like that richness or like that qualitative richness of the information as you would with LCA, at least that's in my personal experience. So, identifying these subgroups, can be very important to really understand, like what it is about these groups that may be contributing to health and well-being or potential inequities or disadvantages. All right, so this was going to come up at some point, so I reached up to it. So factor analysis versus latent class analysis, which one should you actually choose? So I have 4 different points out there to just kind of help you think about, which approach you should take. So of course, everything's going to boil down first to your research question. Like, what is your actual goal? If you're looking to explain variability in your variables, maybe factor analysis is where you want to go. But if you do want to categorize variables into distinct types based on shared characteristics, then latent class analysis is something that you should consider. And the next thing you have to think about, what's the nature of your data? Do you have continuous or categorical variables? And this is where LCA kind of wins over FA in this point, because with factor analysis, you have to have continuous variables, and there is an assumption that they have to be normally distributed. With latent class analysis, it can handle different kinds of variables. It can include continuous or categorical variables, right? Because with latent class analysis, the assumptions with distribution are way more flexible. So maybe that's something you want to do because of that. And another thing you want to think about is the complexity of your model. Like, do you have a large number of variables, and do you maybe believe that they could be explained by a small number of latent factors? If that's the case, and you understand that a priori, then maybe you want to go for factor analysis. But if you feel that the relationships among your indicators are complex and maybe are not as easily explained by a few underlying classes or groups, then maybe latent class analysis is the way for you to go. But again, there's a lot of thinking you have to do before you jump into models, even though it's so exciting to get there. And here I have this quick graph to just kind of guide you in some decision making if you're just going strictly on variables. So here I have a 2x2 of, if you have a continuous observed variable, categorical observed, continuous latent, categorical latent, and depending on where you fall under this 2x2, it can tell you what you might want to do in terms of your analysis. But with continuous observed and categorical observed, if you understand this as being a categorical latent variable, then you can perform some type of latent class analysis if you're using categorical variables. Or if you're using continuous variables, it's known that latent profile analysis is the exact same thing. They just give it cutesy name because of the different variable measurement. So before you even start to think about employing any of these approaches, like, I don't think this is something I have to sell to everybody in this room, right? We all know that neighborhoods are multidimensional. So you have to think about, in terms of choosing your variables, what are the actual theoretical and practical considerations, for choosing the variables that you are using for your research or your research question or whatever it is that you're doing, right? So, yeah, technically you could throw every variable that exists and put it into a model and see what spits out, but you would be really wasting your time, right? Because there are going to be other issues, in terms of model, like convergence issues. So, point is, whatever measures that you include in your latent classes, it should actually make sense. Because, a measure, you may have a measure that exists, for different contexts, different countries, but, do those variables, what do they actually mean for those populations that you're studying? And this is where I actually always talk about, like, we always have to recognize the geographic heterogeneity, of the US population and other populations, because since we are mainly focused on the CDR, I just stuck to the US population here. So, as Rachel already explained, unidimensional applications, the neighborhood determinants of health are just not ideal. So I don't think I have to solve this point to you all, but I'm putting it out there. And of course, your conceptual framework matters. People tend to forget that theory is important. Theory should be driving some of our decision making. So, I put into models or frameworks that, for those of you that want to look more into it and how these complex causal pathways, are associated, between neighborhoods and health. I do recommend reading on the sociological model of health and the life course health development framework. Right? This can help you generate research questions, hypotheses, or ideas about, what you could potentially do with all this amazing and rich data. So one of the things I wanted to draw out here, is this variable example, just to kind of illustrate why context matters and why the way you choose your variables, you should really put some thought into it. So like with neighborhood age structure. So we know that age structures can be particularly important for older adults who age in place because they could potentially influence the provision of health services and facilities, perceptions of neighborhood safety, and even opportunities for social engagement. And most of the research that I read here in the United States, or at least the contiguous, I always get that word funny, the contiguous 48 states, most of that research shows that, a high concentration of older adults is generally associated with better health among those older adults, even for those who are living in socioeconomically disadvantaged contexts. But in Puerto Rico, which is going to be the emphasis of the illustrative example here, as I get to in a bit, because of the context in Puerto Rico, with the increases in poverty and declining economic conditions across the archipelago, migration of family health professionals to the mainland U.S., changes in the family structure, the limited availability of individuals and even services to provide long-term care for older adults, maybe that higher concentration of older adults isn't really a good thing and might actually be representing a better health structure for these older folks as it is found here in the contiguous US, right? So I just want to emphasize here that context matters. Think about what you're doing. So here's a quick illustrative example. Like I said, I wish I had an hour or two to actually get into, all the steps that it takes to do a successful Latent class analysis, but I'll give you the best that I can do with the time I have left. So for the purposes, a lot of us are going to basically start maybe in an exploratory latent profile analysis format, right? Because we may not have actual hypotheses about how many classes you might expect. So we're going to start with an exploratory latent profile analysis. In this case, we're going to do it in Puerto Rican neighborhoods at the tract level. We're going to use R, at least for this example, but I also have code and data to do this. So I will put those both on GitHub as well, and they'll be provided also by Jennifer. So in this case, you could do latent profile analysis or latent class analysis using tidy SEM and R, or if you're using SATA, you can use GSTEM to do this type of analysis. I don't know I don't do SAS or SPSS, so my apologies for those of you who use those programs. I know zero about that. So the present example, I'm going to use some of the data that I took from the Puerto Rico contextual data resource that I have been creating, because one of the frustrating things as the population health researcher who focuses also in Puerto Rico is that there's not much data or leakages in data for Puerto Rico. So I had to put this data myself. So I'm going to take one of those data sets, the 2009 PRCS, which is the Puerto Rican Community Survey 5-year estimates. And again, because I do not have a theoretical reason to expect a certain number of classes, this is just purely exploratory. And I did choose 15 indicators from the 2009 PRCS that encompass these 4 dimensions, like SES, household composition, minority status, and housing and transportation. I don't have time to get into all today as to why these 15 variables were chosen, but just believe me for now and take at face value that these are all related to each other in some way or form for Puerto Rican health. So here's the overview of latent class analysis. Again, it's a very simplistic view, right? Because first you're going to have to choose some indicators. And once you have those indicators, you're going to start estimating some models. And once you estimate those models, you're going to evaluate those models, and then you're going to interpret those models so that way you can get to your amazing final class solution. And of course, this is a very heuristic model of the process. It's actually a much more intensive iterative process, which I have linked here. And this is a hyperlink to an article that talks more about the SMART LCA checklist, which is the standards for more accuracy and reporting of different types of latent class analysis. So you see there's 14 steps outlined here, more than 4. So just so you know that there's just a lot that has to be done to get to that final class solution. So of course, as Rachel explained and everybody else has explained today, you have to get to know your data. You have to look at your data. And I cannot emphasize that enough. You really do have to know your data before you start doing all your fancy modeling strategies, right? So I just put some examples here, some summary statistics of those 15 variables. And again, because this is in PDF, these are not working buttons, and these pages are not going to work right now, but they will post on GitHub. But if I were to have like this sideways triangle here, it would have given you more summary statistics about this variable here. And this one is lists the next set of variables until you get to the 15. You also want to do correlation plots, right? So Rachel showed a version of those correlation plots. Here's my version of those with the variables from Puerto Rico. As you see, the red -1, the blue is to the +1. So just get to know your data. And so again, since most of you are going to be starting off basically at ground zero, and you may not have a theoretical reason to expect a certain number of classes, what I usually do, I start to evaluate 8 classes with fixed variances across classes and zero covariances. And I use that as a starting point because depending on those results, then you can actually do more extensive searches across different model specifications to get towards, that final class solution that you're waiting for or wanting for. And also because again, we are working with different computer systems, laptops, whatever, this is just a way to also reduce computational demands as opposed to just running everything that you can think of. And so when you actually do run those models and it's time to start choosing, which one, should I actually hone in on and focus more in on? So there are statistical and qualitative considerations that you want to take as you're choosing your classes, right? Because again, statistics, they can't tell you everything. There's some interpretation that you have to do. There's a lot of subjectiveness in this as well. So you have AKP's information criteria, which is the AIC, the BCA information criteria, which is the BIC. There's also the sample size adjusted fit. Entropy, you also have to see the interpretability of model solution with assessment of size and uniqueness of each class, and also the low Mendel-Rubin p-value, where you're basically looking at if your, let's say if your 4-class solution is performing better than your 3-class solution. Of course, there are other things that you could consider, but these are the ones I mainly use in practice. But the point is you have to justify the number of classes chosen. So I ran those 8 classes, right? Because again, I have to do this all beforehand or else we'd be here forever. So, I have some statistics here, and based on those statistics, I can make some additional decisions so that way I could look for more in-depth model specifications. You can also plot these statistics, right? So you have your AIC, BIC, and SABIC here, and the lower number generally showing that it's a better class solution. There's also entropy, the closer you are to number 1, it's a better indicator of the separation of classes. So obviously I'm not going to do this here, but I also have to do some subjective assessments of what, the classes are each telling me about. So, considering the statistics and the interpretability of those models, what was the best fitting model for me? In this case, I chose to go with the 5-class model, and then I decided to redo that LPA with alternative specifications. And there's a lot of different specifications you can do, and depending on what you choose to do, again, this is a very computationally intensive process. You have to be super patient. That's the name of the game, unfortunately. When I was doing my dissertation, I remember there was a point where I was running these for neighborhoods, and it took like weeks before I got anything. So here's just an example of 3 different types of, the 3 additional model specifications that I chose just for the purposes of this presentation. And so you see I have the post-estimation plots here. Okay, sorry. Here's the entropy again. And again, I have to also go in the background and do some, qualitative assessments about what each of these class solutions were telling me. And in this case, I just decided to go with a 5-class model with varying variances and varying covariances. And I have the final estimates from that model that are listed here. You could also get these in the cute pictorial or visual form, and they could tell you, where these different classes and where they map onto these individual variables. And also you can, for that way for readers to better understand, you can also put it in a table, right? Like you have your different classes, how many tracks fall under each of those classes, or at least the percent of tracks that fall under these classes. and they give some characteristic information about what's made up in your classes, right? And a lot of this is qualitative, right? Because it's not like, high percent Black population means 90% of the tract is filled with, Black folks in Puerto Rico, right? Like you are doing this subjective assessment relative to the other classes. So like once you have like that information together, then you can start thinking of the fun part is like how would you actually name each class, right? Because when you're writing up your papers and whatnot, like you want to name your classes. Like what are these classes telling you about, your tracks or your different neighborhoods that you have there? And of course, once you run all your Latent classes, do not forget to save your data. Save those estimates because you're going to need that to merge it with your other individual level data. And here are some resources that I have. So I actually have a paper that I published last year on the neighborhood context and all-cause mortality among older adults in Puerto Rico. I used the 2000 decennial census data at the block group level, which has been nice to have versus CHRS. I linked it to the Puerto Rico Elderly Health Conditions Project. And for those who are interested in using Greco, we just submitted the Wave 3 data to ICPSR, and the Wave 4 is going to be finished soon, and that'll be available too. Here's a couple of journal articles in joint LCA to classify neighborhoods, and of course this is not an exhaustive list. I just like these two articles because they really illustrate, how they went through the process to come up with their leading class solutions for their neighborhoods. And of course, for those that need some methodological, background and the uses of latent class and even latent transition analysis, because as you saw with some of the presentations throughout today and yesterday, neighborhoods change. So latent transition analysis is another trick that you're going to want to see or use to potentially use for your longitudinal neighborhoods work. So I really do recommend this book on latent class and latent transition analysis. That's how I learned it. I learned it through this book, so I think it's a fantastic book. And thanks for listening.
Temporally. So my speaker is Jennifer Canavan. She's a sociologist and demographer at Brown University. This is she's a very impressive background in research on neighborhoods and schools and their interactions as two environments in which people develop earlier in life. We're trying to coax her more into the aging space. But she's going to talk to us about something that she's done, not in the context of aging, but we're going to be working together to hopefully provide these kinds of measures in the future in the contextual data resource.
Yeah, but I was just super hyped up after that last presentation. Thank you, Catherine. Nice to meet you too. I should also say my font that I chose, I downloaded a new font with much more narrow, it's different up here, so I feel like it's a different vibe, but I'm gonna go with it. Okay. Alright, so today I'll be showing how a growing number of work that's interested in links between segregation in neighborhoods and a host of individual outcomes are using spatial statistics to derive these measures of neighborhood segregation versus commonly used measures that they used before, like racial composition. So most of this work that's using these new measures, not new measures, but new in the context of this work, come from literature, the population health literature, asking questions about links between residential racial segregation and health, things like how exposure over a longer period of time in earlier life is associated with cognitive performance in later life, how exposure to segregation is associated with self-related health, with behavior problems, etc. Excuse me. So when we're talking about segregation, what do we mean by that? Well, at this point, several decades ago, Massey and Benton tried to summarize this in terms of these five main dimensions of segregation in neighborhoods. The vast majority of work uses indices that focus on those top two dimensions, even as exposure. Far fewer use or analyze explicitly concentration, clustering. The measures that are typically used are measures like the disability index, that's by far the most popular one. The problem for researchers that are interested in links between segregation in neighborhoods and individual outcomes is that these measures are global
entities, the global measures. So they produce a single segregation index for the entire region they're studying. So because of that, each neighborhood has that same value. So obviously creates some problems. And so most work has used in the past neighborhood racial composition as a segregation proxy, which actually is a pretty good proxy, but it doesn't measure segregation per se. So, to sort of get around this, a version of work that I mentioned is using these global neighborhood spatial segregation measures, which does create this individual value for each neighborhood. And specifically, we'll compute the local Gettysburg G-star statistic by collaborators with Collins and NCG. It's actually not that fancy. I'll show you which is a fancy name, but it's nice to think of it as a fancy G. It allows for spatial clustering of a single racial ethnic group in the neighborhood, but it also considers the concentration of nearby neighborhoods. So in doing so, it captures these spatial aspects of segregation that's not captured in these conventional measures of unevenness or isolation. And it's this idea that, this is written in motion, social, economic, political, environmental processes that are not confined to the boundaries of a single neighborhood, right? Neighborhoods are not islands, they're connected to this larger network of neighborhoods which are embedded. This approach can also avoid needing to determine some, a priori racial concentration threshold across multiple state areas that might have much different average racial composition. So the G-star statistic, it essentially produces these score based on the racial composition of one particular group that you're interested in investing unit. We'll say a census tract and the neighboring tracts, and compare that to the mean racial composition of the broader region, let's say MSA. So doing so obviously requires spatial data. It requires calculating spatial weights based on whatever definition you have that constitutes what a neighbor is. And then we can think of these scores that produces as neighborhood concentration scores, because again, it does produce a single value for each neighborhood. Okay, so how do we do this? Well, first we'll take a little step back to understand the concept of spatial correlation. Again, fancy name, simple concept, expresses simply the amount of spatial dependency you have in your spatial data. Correlation here is the key. It's very similar to the correlation indices shown already today. In this case, we're talking about correlation in space. How much is a variable in a particular location correlated with values in nearby locations? And so when we're talking about spatial autocorrelation, testing it are null hypotheses that there is no spatial autocorrelation, but we have instead spatial randomness. That the values of the observed location do not depend on the values observed at nearby locations, and that whatever pattern that we see, the spatial pattern that we observe, is equally likely as any other spatial pattern. So we want to see this, we don't want to see aggregated, we also don't want to see regular. Testing is first, there's two different tests of spatial autocorrelation. They're very similar in the methodologies, that they measure different things, and because of that, they answer very different questions. We have global tests. This is asking, is there clustering at all in our study area? And then we have these local indicators of spatial association, or LISA, statistics, and that asking where is this clustering that's driving this global pattern. So we'll focus on the LISA statistics because it does produce a single value for each neighborhood and identifies where those hotspots and cold spots are. And because of that, we're able to diagnose the units that are exhibiting the spatial dependence with their neighbors, exhibiting or contributing to the global pattern that we see in when we test for global spatial autocorrelation. So the 3 steps to doing this include first, obviously, we have to choose our neighborhood criterion. What is a neighborhood definition makes sense? Which areas are linked? And then when we have our definition for neighbors, we then will construct a spatial weights matrix accordingly, and we'll just run our test. So most the G-star, global Gettysburg star. So the G is G statistic, G that star is a sister of the little sibling of the G statistic. I'll show you in a second how they're related. These use distance space usually for adjacency matrices. I'll say that the neighborhood segregation papers almost always use adjacency based definitions. So essentially the polygon data, any polygon that's touching the focal unit will be considered a neighbor. You can also use, distance based definition, draw a fixed radius around your neighborhood, the center of the neighborhood, anything that falls inside would be considered a neighbor. Or the neighborhood as well, that's also popular. So I'm going to follow for this example, most folks segregation number 2, which is I'm going to define neighbors using a Queen's first order criterion. So using my square shaped metropolitan area right here with all my 16 census tracts. So if we look at the middle, so the neighborhood 6 in the middle, we see that all the lines and vertices that are touching that becomes, those all are identified as neighbors of neighborhood 6. We'll do this for every single unit within the 16 unit grid. We'll then take that, place it into the common row standardized weights matrix. We have 8 neighbors for neighborhood 6, so these all get a weight of 1/8. They all sum up to 1, so the row, the rows up to 1, nice and clean, right? So we did this for all the neighbors, neighborhoods, and we end up with a matrix that looks like this. And so now we've got our neighbors defined, we have our weights matrix, now we're ready to calculate this. I'll kind of start by saying, so this here is the formula for the G statistic. So the G statistic and the G star are very, very, very similar. The only difference is that the G statistic excludes the focal observation and the calculations of only computing the spatial lag of neighbors values in this, and G star includes the focal unit. So if we're talking about segregation, obviously we're not concerned about that focal unit, we're concerned about that neighborhood. So pretty much every study will use that G star rather than the G statistic. So the formula up here, you'll see different variation of it. Essentially what we're looking at in the numerator for the G star is this is just the weighted average of the value for whatever value you're looking at, say racial composition for the focal neighborhood and all of their neighborhoods. And the bottom we're just dividing by focal value. And so if we are looking at a non-standardized G, just sort of as a population of all X values in the study area accounted for by the neighborhood itself and its neighbors. But usually it is standardized. Always, you kind of want the standardized version. It's easier to make categories this way. So in this case, it produces a Z-score, which essentially represents the extent to which the racial composition of the voting unit neighborhood and its surrounding neighbors deviate from the mean composition of the larger study area, say an MSA or the city. And so I'll put this in practice. I'll show an example from New York. So I'm using here 2012 data. Neighborhood racial composition, 5% Black. My neighborhood is defined as a census tract. This is an actual connectivity map of using a Queen's first order criterion, showing all the connections between the neighborhoods within New York City. And so I'll start out by just simply plotting neighborhood racial composition here in this map. Just using cut points. I can pretty much see where the hotspots are already. I can see that. Very dark areas, places we would expect. But of course, we want to test this. And so to compute the G star, I am going to again use the Queen's first order criterion here. I'm implementing this in R using the SPDEP package. Local G here is the call. So if you look at the top, local G is the call, the val is my value, val is neighborhood composition there, which is Black, proportion Black. I am simply so here I'm just pretty much making weight matrix on the fly. But the important part here is this right here includes self. Following because basically distinguishing between the G statistic and the G star. So we want to include the self, we want to include the neighborhood, the local neighborhood in the calculation here. And then we'll reduce our value, our G star values. I guess some quick summary statistics there. You'll see that the G stars that you get from our in this approach are standardized, essentially G scores, but we can map them on the left and use whatever cut points you want. Here I'm just using cut points based on their more meaningful based on critical values of significance. You can use whatever you want. And so again, these are measures of concentration or lack thereof. Again, we have the darker areas or the hot spots, the darkest blue are the cold spots. So measures of concentration or lack thereof, and some attributes in this case are some black in the study area. In this case, the study area is New York City. Strong positive values, and you get high relationship, negative as well low. So attributional similarity can take on both positive or negative G or G star values. And in terms of thinking about spatial segregation, we can think that relative to the racial composition of the larger study area, in this case New York City, higher positive G star scores indicate more representation. Scores near zero, perhaps indicating racial integration, and then lower negative scores would suggest underrepresentation. And so, because of the way this is constructed, this statistic reflects both contextual and spatial aspects of segregation. Higher the G star statistic, the larger the difference right, between the neighborhood racial composition and the larger study area. But also, you're going to have a larger G statistic. You're also the neighborhood is also surrounded by neighborhoods that are segregated as well, versus those not surrounded by less segregated areas. Okay, so what can we do to put this in our models? We can categorize this in various ways. Having z-scores makes it kind of a lot easier to construct categories that are more meaningful. So we can take the approach to a lot of neighborhood actually search and approach today as well. You've heard the entire presentations by ordering segregation into these quintiles. So, sort of a lot of neighborhood observation research or neighborhood research that tries to understand the neighborhood information exposure a child, for example, has. We'll construct this like a category indicator. We can do the same thing for segregation too to see how the extent to which somebody is exposed to segregation. We can categorize in all sorts of ways, high, medium, low, using and use z-scores to create categories based on significance. I should say that a lot of managers use a low cut point, so that should be the other direction, less than zero. This is because usually the focus is on concentration rather than underrepresentation. That's one reason. Another reason is there tends to be fewer census tracts that have a z-score that's less than 1.96. So usually they'll just take everyone. Anything less than zero will be considered low segregation. We can also use the G-star values as a continuous variable to the treatment. So we can use it in prior work. And then we can also have longitudinal data categorize these neighborhoods over time to track changes in segregation level, as I do, or look at their segregation trajectories. And so just a couple quick examples. If I were to say categorize this as high segregation, moderate segregation, no segregation, this is just literally taking top two categories up here, sticking them into high and moderate segregation categories. Everything else is coded as no segregation. We see how it's distributed here, and that would be one approach to doing it. One that's more common in the existing literature so far is categorizing neighborhood observation. If their z-score or g-star value is above 1.96, moderate is between 0 and 1.96, and everything else below 0 would be low. And we see a little bit of a differentiation pattern here. Obviously, more neighborhoods are categorized as segregated using this approach. A couple of things to consider before I wrap up. The choice of weights in neighborhood matter, that matter. As everyone also has noted, you should drive these decisions as much as possible. You're gonna have different results if you choose a distance or adjacency based matrix. You're gonna have different results depending on the distance threshold you choose. 10K versus 2K will obviously increase the number of neighbors in one sense versus the other. Also, the study area matters because it's part of the calculation. This is going to matter being a significant hotspot, and the entire metropolitan region of New York is obviously different than being a significant hotspot in New York City. I showed you an example in R, the other packages you can use in other programs. You open up and click a hotspot analysis tool in ArcGIS, as well as data using the user written command that you stored. It's a little more restricted here in terms of weights, matrices you can choose, but it is pretty straightforward. And there's some resources here. I'm happy to share slides with folks that are interested. Just email me. And that's it. Thank you.
Be more sophisticated spatial work. This is why you need teams because you need people who have different levels of expertise. Thank you for taking me all the way back to graduate school and Geoda. Okay, and then our last presentation, I'm just going to go over a little bit. Lunches here, some starving, I barely fed you at breakfast. You could get your lunch if you want. But our last presentation is now moving from thinking about creating measures in a very spatial sense to thinking about creating measures in a temporal sense. And Christina Gang is going to be giving this presentation. She's a postdoc on our Tier 2 multidisciplinary training in gerontology program. And so she has been doing work raising air pollution and cognition, and now she's moving into more of the biomarkers. She's going to talk to you about some measures she created for some of her work using measures of pollution. Okay, I'm gonna keep this out if you can't hear me. So yeah, I am going to be talking about sequence analysis for air pollution over time. Just a couple of motivating questions that I went through in my dissertation just to help you think about your data. If you have a long history of data, are you not sure what the exposure window is, and you want to capture more complexity than a mean or a median. Things like type, order, timing, duration. Well, sequence analysis can or maybe can solve this problem. For my research question, my dissertation, I was looking at air pollution and cognition and Alzheimer's disease dementia. So I was interested in PM2 and N2 specifically. So things like type PM2 or N2, order PM2.5 to 21st, timing, we're not sure when the exposure matters, duration, or how long the exposure matters. And we're trying to really get a video of a trajectory. And we are assuming that all these things occurred during our study window for this presentation would be from 2000 to 2010. So that's a big assumption given my okay, I didn't realize the graphics. Okay, so there are 2 points I want to kind of drive home for sequence analysis. Is an analytic technique summarize differences in ordered events. So this can be base pairs, pairs, or policy. And that's kind of like the biggest thing is you have to categorize your data initially, and which may or may not work depending on your research question. I'm going to go over this a few times, so if you don't get it the first time around, then there'll be multiple times to look at this. Okay, so what I have here are 2 different person trajectories. You have each row is a person, and you're going to categorize air pollution into mutually exclusive states to form individual level trajectories. So you've got person 1 here, it's 11355, person 2 1155. And then we'll define substitution costs, and this will be based on your transition rate. And so if you have very common transitions, so like going from high pollution to middle pollution to low pollution, that's going to be more common than going from a low to a high pollution state, right? So for rare ones, you're going to extend a very high substitution cost, and for very common, it's a lower cost. And so as you can see here, the differences are in this third state, it's substituting 1 and 3. And then from these, we will do this against all the trajectories in your analysis, and you will have a disability matrix and the cost associated with transitioning from one trajectory to another.
So the output of a sequence analysis is a dissimilarity matrix. You can do a lot of things with this. What we're going to do is a cluster analysis. So does everyone follow me halfway so far? Great. All right, so the other part I wanted to emphasize with sequence analysis and I would like to summarize differences in sort events. So we have a few states such as low, medium, and high, and you measure over time. So for me, we're looking at 10 time points. This would yield over 59,000 different sequences, right? So if you have this many different sequences, you would be considering each of these a different exposure trajectory. Trying to reverse something like that would be very computationally difficult, probably wouldn't work. And worse, you can't even really interpret it or understand it. So the real power is that you can summarize these into your dissimilarity matrix. So it allows us to find the dissimilarities between your trajectories. Okay, so we're going to do an application of this for my paper 3 dissertation. So the first step, we're going to do the sequence analysis, which will be categorizing my pollutants, PM2.5 and NO2 concentrations into low, medium, and high, based on the 25th and 75th percentile cutoffs from 2010. So you'll have statements like high or high PM2.5, low NO2. We'll follow this up with a cluster analysis and then finally the regression. I'm going to focus on the sequence analysis for this. Okay, so here on your left, you'll see just a quick summary of pollution in 2000 and 2010 for PM2.5 and NO2. I highlighted the cutoffs that I've used, the 25th and 75th percentiles, and then we'll create mutually exclusive states. So you've got high, high, medium, high, low, so on and so forth. Okay, so this is what your data set will look like. So each row is a participant or census tract, depending on whatever your unit of observation is. And I've got 2000 to 2007. We're going to 2010, right? I've given you a snapshot so you can see like the top person here starting with high PM, high NO2. And then in 2003, they have less NO2 exposure, goes back up. So you got this for everyone in your data set. I'm looking at and has this will be 6,750 people in my data set. Okay, so this is what I think is the real power of sequence analysis. It's called an index plot. On the x-axis, you have time, so 2000 to 2010. On your y-axis, what I've done here is I have done every air pollution trajectory in the United States, so all 72,043 census tracts. I've sorted it by 2010. Usually colors represent each of our 9 states that we had in the previous line, and so I color coded it where the darkest colors are the highest air pollution states. And so you can see over time, air pollution decreases, which is what you expect, which is what we've seen in previous lectures. And you can also see that if you're looking at 2010, that is an incomplete picture, right? This is what I did for my paper too, so it hurts me too. But if you're going to take a meter median as a long-term proxy for exposure, it's really not capturing the entire thing, right? This is what I think is so powerful about sequence analysis. Okay. The next step would be a cluster analysis. I'm not going to get into this too much, but there's a lot of ways you can cluster. There's a whole field on it, right? I've showed a few different indices in which people will determine the number of clusters. There's like a silhouette width that I just want to compare as. There's G, serial correlation. They all converge around 9, which is what you end up with. So you can also look at the clusters. After you cluster, you can look at the index plots by your clusters. What you want to see is maximum homogeneity within the cluster as different separately, right? So cluster 1 and 2 are clearly high exposure categories. Cluster 6 is clearly a low exposure. Yeah, that's pretty light, but it makes sense. And then one of the cluster analysis or the you got kind of like a kitchen sink down there for cluster number 9, or you kind of put everyone left over to its class. As you can imagine, there's a lot of ways in which you have questions following how your clusters perform. I'm only going to show one way because it's very overwhelming and we spent an entire certification on like 6 slides of these. So all I've done is a table 1 on the clusters. I've tried to order them. There's a lot of information on the slide. So cluster 1 through 9. So I'll point out cluster 1 and 2 are all the way on your left and have the associated table 1. Cluster 6 is your low and right here. And the only characteristic I wanted to point out on this side were there's differences by race, ethnicity, as you would expect, and urbanicity. So cluster 2, for example, has 99% urban tracts, whereas really at cluster 6 got 0%. You can do a lot of other things like plot them, obviously, you can map them, but that's not the focus of this talk. Okay, and finally, right? You can do a lot of things. I've regressed them, so it's just a cluster, my outcome of cognitive function. And yeah, does that make sense? Yeah, okay, great. So I do want to just circle back. This is not just for exposure, it's a descriptive analytics technique. So you can do it for the exposure, you can do it for the outcome, depending on the question. I will you have to make mutually exclusive states, which again doesn't make sense for everyone's question. You have to decide what to do with your missing. This is air pollution, it's nice and clean, you have all your data from 2010. Previous applications from social sciences, if you're trying to do it for education or occupation, you're gonna have a lot of missing, and that's going to make a missing category, and it's in clusters. That's kind of weird if you don't know how to interpret that, right? So you're gonna have problems to compute, which is going to be very time intensive from what I see in the house. You also want to consider how you want to use time. So in order to create your similar matrix, I wanted to keep time very strong, so I used to call it dynamic hamming, things like optimal matching, which I know is very popular in social sciences. And then finally, going to the cost mean. This is one of the big things about sequence analysis. I'm still thinking about it. I do think it helps to think about why sequence analysis was created originally in evolutionary biology to kind of see the differences between DNA sequences. All right, so you have a cost in their field is a one for insertion, one for deletion, and two for substitution. It makes sense, right? So in applying it to air pollution, how can we validate that, and it does make sense. I would like to thank my dissertation committee on the left and then my USC team on the right for supporting this work, and then as I and here are some references you can use and some papers that I found very helpful. Please reach out for